Okay, so welcome everybody to the first of a set of webinars that are towards IMVC 2026. And the idea is to have like a few or every month, like a webinar that will introduce us to another exciting domain. So our first speaker is Ravid Shwartz-Ziv. Is assistant professor at NYU. And I looked a little bit, Ravid, at your resume, at your LinkedIn resume. So you did your PhD in the Hebrew University of Jerusalem, and you've been working in Intel, and I think also in Google, or
Yeah.
Yeah, and now you are also partly working in a company one which aims to provide some kind of agentic AI to be used in day-to-day activities, something like that. And Ravid, I think it's very interesting to follow him on LinkedIn. He's writing interesting posts, and I think that you wrote some pretty cool papers. So I think that, yeah, we can get started. So Ravid will talk about the compression paradox and why AI and humans see the world differently. Ravid, the floor is yours.
Thank you. Thank you, Chen. Yeah, so today I will talk about several recent works projects that we have done. And mostly we will talk about compression. I will try to explain what does it mean compression and why it's important, and how can we compare between humans and AI models in this from this perspective. Okay, so first of all, I want to thank for all my collaborators. This is just a sub list of them. They basically did all the work, and they're really great. By the way, if you have questions, I don't see, but you could probably chat. You can write in the chat.
Yeah, so if you're fine with having questions while we're doing that, I will keep an eye on the chat and we'll ping you.
Yeah, sure, great. Yeah, so if you have questions, ask them. Okay, great. So I will start with let's say the abstract, like the bottom line of this talk will be about compression, and about I will try to convince you that communication is fundamentally an act of compression, and what we want from a good communication and from a good representation of our models is compression. And I will try to look at it from the point of view of information theory, and I will try to take some tools from information theory in order to come up with some guidelines and principles, and to compare, or like to estimate what is the gap between human and artificial intelligence. Okay, great. In general, what I like to do in my research is to do two things, like let's say two parts. One is to get good understanding from the representations, to look at the representations of the models. It can be on the intermediate layers, or it can be in different settings, and to use these insights and this understanding in order to make better models and to optimize our models. So if you're talking about information theory and in general, and also machine learning, we should start with the father of machine learning again, information theory. This is Claude Shannon, that said that the best approach is to try to look on the problem from many different directions. And this is exactly what I'm trying to do. Also here, I will try to look on it from different directions and to see how can we unify them. So compression, again, I will tell what does it mean compression, but all of us had like some intuitive understanding what does it mean, but we'll try to look on it from different perspective. And as I said, we want to understand the differences between human and AI and their representations. Okay, so I will talk about, I will try to talk about 4 different projects. Probably I will not have time, but we will try. I will start with looking and comparing LLMs, large language models versus humans, and how they look on categories and how they represent categories and how they have a different meaning of categories. And then I will talk about debates and why debates and debates competitions are so good and so a great area if you want to compare between AI and humans and what we can learn from that. And hopefully I will talk at the end about chess and how human and AI are different or the same, has the same representations in chess. Okay, let's start with what is a good representation. So this is very fundamental problem or fundamental question that people are asking for quite a long of time. And this is very fundamental because like at the end, all of us has good intuition, right? Like we want, what does it mean even a representation or like good representation, but it's really hard to define it and and to understand it in more rigorous way. So I will try to look on it from information theory perspective, and I will try to formalize the representation quality from information perspective. So let's assume that we have X. This is our data. Okay, it can be an image, it can be text, it can be whatever you want. We have some training data, and now we have label. Let's assume that we have label data. This is again the simplest case. We have for each X, we have the label data. It can be classification if we have dog or cat in the image, or it can be some, I don't know, if this sentence is good or bad, or sentiment analysis, thing like that. Okay, and now we want to learn a representation. We want to learn a model that will take this data, these samples, and we'll convert it to some representation that will give us good prediction about the labels. And the question is, what does it mean, good representation, or like what we actually want from these representations? So one way, as I said, there are many answers to this question, but one way to answer this question is from Tali Tishby 25 years ago. So this concept called the information bottleneck, this principle called the information bottleneck, that gives us very concrete answer. Do you want good representation? Okay, let's look on the information. Let's look on the mutual information between the variables. Okay, so the mutual information is how many bits you have from how many bits one variable tells you about the other variable, how much information they shared in common. Now, so the information IXZ is the mutual information between my input and my representation, and the information between Z and Y, okay, IZY is the information between my representation and the label, predicted labels. And the concept says something very simple. You want good representation, so you need to compress X as much as possible. You need to compress your input as much as possible, and at the same time, you need to keep the information with the labels. So we have this trade-off between compression, the compression of the input, and the prediction of the labels. Okay, and in more intuitive way, we want to keep the relevant information. We want to keep only the relevant information in our input. So think about dogs versus cats. Okay, you have a classification problem that you want to distinguish between dogs and cats. You have a lot of images of dogs and a lot of images of cats, and now you want to classify them. Now, if you keep all the information in your image, so essentially you need exponential number of images in order to classify it, right? Like think of it that like you have one dog, okay, the same position all the time, but with different backgrounds. So in principle, you need all the different backgrounds to learn to get all the different backgrounds to have all the different backgrounds in order to classify everything correctly, right? But if from some reason you compress the background, you remove the background, then you need only one image in order to classify it, right? Because think of it, if you have a machine that remove the background, then every image you remove the background and boom, you have the same image all the time, okay? So this is exactly an example of compression and intuitively why compression is a good thing. Okay, so they formalize it in a very elegant way. So now more, let's say more rigorous, we can say that compression gives us or brings to better generalization. Okay, so the generalization error, generalization gap is a difference between my training and my testing. Okay, this is how much I can the performance compared to the performance that I have on out of distribution data, thing that I didn't see during my training, and we actually can show that if you want a good generalization gap, if you want a small generalization gap, right? You want to reduce the gap between the training and the testing performance. So you actually need to compress. You need to reduce the information with the input. Okay, and there are several bounds like that, but the idea is simple. If you compress, if you reduce the information with your input, then your generalization gap will go down. Okay, your generalization ability will increase. Okay, so this is why we want compression and why we want the prediction, or why we want to increase the information with the label. This is quite obvious because basically this is the information that we care about. This is the information with the label. Okay, it's, you can think of it as the accuracy or something like that, and it's this is something that we always train on. Okay, and again we can see this compression thing for many cases. You can think about the huge data set, a database that you want to compress, and there are different names from different perspectives, as Occam razor, MDL, Kolmogorov complexity, things like that. All of them are basically the same thing, that compression is some kind of learning and what we call, or we can formalize as intelligence. Okay. We also see, we also can look on compression as sorry, we also can look on communication as kind of compression. Okay, so think of it as like you have the source, right? And you have the destination, you want to pass some information to the destination. So you must pass it through a channel. And this channel, okay, helps you to compress. This channel compresses the information, hopefully the irrelevant information that you don't care. And this is the only way to pass information. And you can think about different fields that you need to pass information, and communication and language and all a lot of different use cases that we need. Okay, so now let's talk about comparing. If we want to compare between LLMs and humans, how they deal with different meanings, so like how they look on concepts, and what is the representation and what is the information they save or keep when they are dealing with concepts. Okay, and again, we wanted the main question that we wanted to ask in this project is very simple. Like, do LLMs have the same representation as humans when we look or when we talk about concepts and some hierarchical concepts? Like, we have some clusters of meaning. Okay, and as I said, we try to look on it from information theoretic perspective.
I have a quick question, Ravid, because so what you
Yeah.
reviewed so far, the compression as a means to really I would say transmit the most meaningful information, or to keep the most meaningful information. So what you've talked about so far was related to machines, not to humans.
So this is like general, okay? Like it's not even related to machines, right?
Okay.
Like it's just general concept that you can ask what is the relevant. Look, that I didn't talk about what does it mean, like what are the labels, what the labels are, right? Like what is the relevant information. But this is a general concept that every time that you can say, okay, this is the relevant information, these are the labels or whys that I care about. So now I can derive the optimal representation. And of course, like again, I hide all the things that related to, you need actual probabilities, for example, like the true probabilities and all these things that are that I don't want to like to get into them, but you have a lot of things that are undefined or like unclear, like what they actually mean with humans. But this is very general concept.
Thank you.
Okay, more questions? Okay, great. So yeah, so the next thing is as I said, like we try to look on concept and how humans look on concepts, and the idea is to look sorry and and the idea is to look on concept as kind of like compression. Okay, so like for example, if you're Robin and Blue Jay, this is the concept of birds, right? And this is how humans think about concepts. And also we have some typicality. Okay, so Robin is a typical bird, and penguin is a atypical bird, right? And we have this structure inside each concept. If you want to have this structure that separate between typical of these concepts and non-typical cases. Okay. And at the end, we want to look on it and we want to try to quantify, okay, how much humans versus LLMs are compressed these concepts versus how much they store the original meaning of these terms. Okay, so we have three different three main questions in our project. One is to try to see if LLMs have the same clusters as human, or like what are the categories that LLM have versus the categories that humans have, and if they are aligned to each other. Okay, and the second one is inside each category. So now let's assume that I have these categories. So inside each categories, do LLMs actually capture the same category, the same typicality of humans? Okay, again, the Rubin versus Penguin. And the third one, and maybe the most interesting one, is how actually LLMs versus humans balance this trade-off between how much you store the information you think about the, I don't know, birds, Reuben and penguins as kind of birds, okay, and you throw out all the details of them versus how much you store all the relevant, all the information and all the semantics of these terms, okay. Okay, how we did it? We took different cognitive, classical cognitive experiments from humans that people ask humans. Okay, what is, so now you have a penguin. How far is it from bird versus how far is it from other categories? Okay. Um, and by the way, we upload them to Hugging Face. If you want, you can play with them. And these experiments actually helps us to build these. Think about it as a graph of answers, or like the distances between categories, and inside each category we can also quantify the distance, or like generate or like construct this graph. Okay, and now we took different models, different LLMs, a lot of different types, both encoder only models, decoder only models, like others, weird things in different sizes. Um, and we look on the representations. We did the same thing. We insert these terms, and we look on the representations. Okay, and we try to look on it from the information bottleneck principle. It means to look on the information that they store. So in our case, again, the information bottleneck is very general concept. So in our case, we have two terms that we can balance. Okay, one is the complexity of the representation. So think about it as, so C is like what are the categories that we actually have. Okay, so the complexity of our categories, how much we store the information from the input to these categories. And the second term is the distortion, how much we can reconstruct the actual original terms from these categories. Okay. So the first term is compression. Okay. We cluster the points together, and the second time is the distortion, is how much we have the fidelity of our representation. Okay, and as we have lower, we are lower in this trade-off, we are more optimal in some information theoretic sense. Okay, we have more efficient representation, if you. Okay, questions?
Yes, I have a question. So would you say that it's because what it reminded me is like when you measure inter and intra variability between groups. So is it like some can you look at it as some kind of a path towards some optimization problem where you want to maximize the inter-groups variability, but to minimize the intra-group variability?
Yeah. So in general, like I like to think on information, at least in the empirical case, when you look at models and things like that, as kind of clustering at the end.
Okay.
This is what happening, right? Because that we can reconstruct from the representations, like more theoretical way is is that we can reconstruct from the representation everything, right? Because at the end, like these are like all digits, and they are like, I don't know, like it can be like 32 float or something like that. So we can construct everything, but as I see it, everything is clustering, and the question, or like the measure that we are using is mutual information, but we are looking on the clusters and how they separate from each other and how they organize inside each cluster. Okay, so under like some assumptions, you need to make some assumptions to Gaussian or things like that in order to fully formalize it, but besides that, this is very similar then.
Thanks.
Okay. Okay, so the first question is, do LLM clusters are aligned with human clusters? Okay, so we took the LLM embedding, token embedding, we did k-means to cluster them, and then we compare the clusters to humans. Okay, and we compare it to some random baseline to see if like the clusters are aligned more than random clusters. Okay, we look on different methods, and so there are a lot of ways to measure actually information in deep networks, and there are pros and cons for each one of them. It's not clear what is the optimal thing. There are a lot of papers about it, and this is why like we tried several of them. Yeah, and again, we want to see the alignment between the embedding of LLMs versus human. And what we have found, so here the y-axis is the information, and the x-axis is the model size, okay, for different model families. And what we have found is that there is alignment between all the models. There is more alignment between the models and humans versus some random baseline. And what is more surprising is that BERT models are much better. Like they are much more aligned to human representations. Okay. The next question that we wanted to ask is what is okay, so we know that now the concepts or like the categories are aligned with each other, but let's try to understand the semantics, the fine-grained semantics inside each cluster. Okay, so we basically calculate the cosine similarity between different terms. And we compare it to humans, okay, and we look how and we look the correlation with some human rating. So as I said, so robin bird has high similarity versus penguin bird should have like lower similarity, right? This is what we expect from as humans. This is what we will have. So we want to see if also like LLMs have this property. And what we found is that we actually found that the correlations are quite weak and not significant. And LLMs don't have it. They don't have these prototype concepts. Okay, so the internal structure, the internal structure for each category is very different from how humans structure their categories.
But Ravid, I have a question because and I think that this question is with me since the beginning of the talk. So, but if you assume that you are using, I don't know, if let's take for example like supervised machine learning where the ground truth is provided by, let's say, humans, and you are, I don't know, and even when you have things like self supervision, etc., then somehow I would expect that when you are creating some kind of an embedding space, being it LLMs or anything else, that things which perceived as similar in the ground truth would also be like close to each other in the embedding space. So I would say if you've built some kind of a solution which relies on where your ground truth is somehow the human way of perceiving things, wouldn't you expect that your embedding space will reflect that? Because I'm confused. Otherwise, I mean, so shouldn't it be the case when you have supervised machine learning for sure? And otherwise, if you don't have supervised machine learning, then does it mean that when you don't have supervised machine learning, then you have a problem because it will divert from human interpretation?
Yeah, so but like this is not supervised, right? Like
Yeah.
all the things that we look on them are like kind of unsupervised. Like we didn't train the models to have these properties, right? So if you will train a model, I assume that like if you will train a model to have this property of of similarity, right? That like that or typicality, sorry, like if you have this property, so yeah, probably the model can learn it. But I think it's interesting to that when you train a model, when you ask now LLMs, does it have this property, even though it works really well, right? All of us know that LLMs are really good in some aspects. They don't have this property. Okay, they don't think, or like they don't store the representation in the same way as humans do. And why is that, and do we need to fix it? Is a good question. But yeah, we don't have labels for it, like, or we didn't train the models to do it, and then this is why they are not doing it.
Yeah. There is another question from Gadi. Hi, Gadi, thanks for the question. And Gadi is asking, is the change between LLMs and human brain is due to different architecture, or since with humans, we have constraints such as computational limitations?
It's a great question. I don't know. So I must say that like I did my PhD in computational neuroscience at LSEC, and since then, like every time that people are trying to understand like the differences, like to say that like these like models are behave like that because of this, and humans behave like that because of that. I'm a bit suspicious. It's really hard to know. Like at the end, we don't understand LLMs and we don't understand humans, and we don't understand why humans behave like that and LLMs behave like that. If you ask me, the best thing that we can do right now is to try to show the differences and the similarity in the behavior and in the representation of these things. Like to try to understand why is that, and how can we fix it, or like maybe we don't want to fix it. Like these are good questions, but we are not there yet.
Okay, so there is one more question. Timna, hi Timna. Do you know if human brain representations correlate with human perception? Okay, so I think that you related to that a bit. Meaning, is the self-reporting correlated to the actual brain signals?
Yeah, so in general, yes. There are a lot of works that are trying to show it. Again, it's hard to say, like in some cases that's true, in some cases that's not true. And I did talk about it, but like in principle, when you say, okay, so what, like when you try to compare AI models to human, you can look on different levels, right? Like you can say, okay, I'm trying to track to measure the EG or something like that, or like maybe to patch neurons and to look on the spikes of the neurons, or to look on more cognitive aspects of it. And it's really hard to say what is the right level. And there are pros and cons for each layer. And one of the things is, yeah, like how much it's correlate between the different layers, right? Like between the signals and the spice and the cognitive side. In general, there is a connection or correlation or something like that, but again, there are a lot of cases that there isn't.
Okay, so there are more questions, but maybe I'll let you just talk a bit more, and then we will
Yeah,
address
we can
them.
if you we can
Okay,
ask, or you can
okay,
ask.
okay.
That's fine. Like,
So there is a question from anonymous attendee. Wow, this is mysterious. Does compression help AI system retain information or context over long duration? So does the compression
yeah.
actually help the AI system?
Yeah, so it's a great question. We have a lot of works about compression in LLMs and in which cases it works and which cases it doesn't. And we can talk about it really for hours, but in general, it depends on the task. It depends on the task, and it depends on the dynamics of the learning and the dynamics that you want. Compression, again, it's helpful in some cases, and probably like we need a compression in order to learn. Actually, like the models need to compress before they can learn something. Um, but yeah, it's difficult question. We don't have a clear, unfortunately, we don't have a clear answer when and why compression helps for models, for artificial models.
Okay, and Shmuel is very practical. He's asking how LLM can support humans in emergency situations such as wars, nature disasters, diseases. Yeah.
It's a good question. I think that like the thing is that like LLMs can be very good without be similar to humans. I think this is like we don't need to look or we don't need to mimic or like to try to align LLMs with humans if we want to solve these problems, right? Like we basically need to train them in order to solve these problems. They don't need to be related. And I think that we are quite good in these cases. Actually, I don't think like this is something that it's very difficult, at least in the current state that we are in the LLM revolution.
I think you can now move forward. Let's continue.
Okay, great. So our third question that we wanted to ask is is to measure the compression, right, the efficiency of the representation, okay, and to measure this trade-off and to compare and to ask which representation, LLMs versus humans, is more efficient, okay? So we apply the objective function that we looked before, and we compute the human category, the LLM clusters, and then we looked on different level of granularity, like on different level of compression, if you want. Okay, so remember the objective function measures two things. One is the complexity, okay, and how much information we throw. And the other one is the distortion, or like what you said about the intra-cluster variance, okay, under some assumptions. And this gives you the efficiency, okay? This gives you the efficiency of the representation, or like how optimal is it from information-theoretic perspective. So let's start with some previous work that we have done about the efficiency of LLMs in general, okay, and why we actually what we actually see in the representations. So imagine that we measure the information of the representation with the input and the information of the representation with the labels, these two terms, in each layer, okay? and we measure it over all the training process. So we start with very random representation. We measure the information, and then we go along the training process. So what we found that we have two phases basically in this training process, and this is training process without any organization, like just SGD on vanilla networks. Again, it's not related to LLMs. Just this is for vision, but also in other fields. But it's not related to humans. Just machine. So what we see, you see that we have for all the layers, they increase their information with the labels. Okay, you can think about it as fitting to the training data. And then at the second phase, this is most of the training time is compression, and they compress the representations. And at the same time, they have better and better generalization ability. This compression gives them better and better generalization ability. And basically, all the layers compress the representation till they converge to some very good solution. Okay, so we have these networks, these artificial networks. We know that they are very efficient. They know one of their secrets is that they have this internal mechanism of compression, very strong compression. Now let's look when we compare them to human. Okay, so y-axis is the efficiency, and x-axis is the number of clusters. We can play with the number of clusters that we check. And what we've found is that so each line is a different model, right? And lower is more efficient. So what we've found is that basically LLMs are much more efficient. All the models are much more efficient than humans. Okay, the black line is the one for humans, and we found it across many models and data set. The representation of LLMs is much more efficient. They store less information, if you want. They store more information, but get the same results. Now, why it matters? What does it actually mean? Okay, so when you look on the entropy, so as I said, like higher entropy means more diverse cluster, right? The clusters are contain more information, if you want. Okay, and they keep more details inside each clusters. And we can see that humans consist higher entropy. They have more relevant, they have more details that may be not relevant to this specific task, right? But it still contain a lot, but it's containing a lot of information. Okay, these classes compared to LLM that are very efficiency, their classes are very clean. And at the same time, they very good, and they use only the relevant information for these classes.
Ravid,
Okay.
a quick question again from anonymous attendee. So asking how is L computed for humans?
So we have we have the distance, as I said, like we have from these cognitive experiments, we have distances between the terms and the categories. So we can look on it as graphs and calculate this information for each level of granularity.
Yeah, and I have an additional question. So again, thoughts that came to my mind is that we humans are much more, I would say, affected by noise. And we are, I mean, even emotion, I mean, even emotions can be considered as noise. So we are not always looking at, facts and data, but also what is our attitude towards the facts and data. And this is really, and I guess that LLMs don't have any, at least as far as I know, they don't have any emotions or prejudices towards the data. So they are not as attacked as we are as humans by so much noise that we have to digest somehow.
Yeah, exactly. And then this is the question, like what we actually want from our representations, right? Like humans has a lot, they have a lot of other types of knowledge, and they collect information all the time, right? And you have a lot of different goals, right? It's not just like you have one goal that you can throw all the irrelevant information, right? Like you need to store this information because you have multiple goals. So yeah, it's exactly this, but it's less efficient. And again, I just want to say again that the question about efficiency is very complicated, because when you talk about efficiency, when you talk about compression, at the end you need to ask yourself, okay, what is the goal? And now if the goal is to construct these categories, this is one thing, but if we have multiple goals, then it's not efficient. That's fine that it's not efficient for one task, but it's maybe efficient for multiple goals. Okay, so you need to ask what does it mean. Okay, great. So as I said, the LLM minimize the redundancy, they maximize the gratitude, the prediction ability, and they basically very good in compression versus humans that preserve the context. And this is enables some generalization to other tasks, right, to multiple tasks, but at the same time, it's less efficient representation. Okay, so to conclude this part, so that LLMs are they have quite the same categories as humans, conceptual categories. They align with them. We see that inside each category, the fine-grained structure is very different. Okay, we don't have this typicality concept, and we also see that LLMs are optimizing, or like their categories are much more efficient, and they compress them in a better way versus humans that contains a lot of information that for one specific task it may be irrelevant, unnecessary. Okay. What does it mean for AI for the future? It's a great question, but I think like then it's really hard to know, and it's really hard to know how can we use it. We can use it to try to develop some better scanning laws, for example, in order to make it more efficient. We can look on some architectures and solutions that will explicitly align human concepts and human concept representations and LLMs. And we can try, and I think this is the more important part, we can try to balance between these statistical efficiency of LLMs and more flexibility and richnesses that we see in humans. And I think this is something that we need to take into account and to try to address it in a better and maybe an explicit way. Okay. So yeah, so this is again, there are a lot of questions that we can try here. Some of them like we are trying to solve right now. For example, to look on human on vision models, or like vision language models, right? Or like to get more richnesses, more dynamic embedding, like how the context affect it, right? Here in this in this study, we only looked on static embedding, so we may want to look also on something like that. Again, a lot of future directions. I don't have a lot of time, so I will only like mention it briefly.
And we do have some questions also as well. So,
yeah, I will say just like 2 sentences about debates.
Yeah, sure.
And why I think it's cool. So debates, we have 2 recent works about debates. that you should read. One is a debate data set, a huge debate data set with almost 4 million documents that we clean, and then we train models on it, and we show that how compression and how the debate is a very elegant framework to show compression. Because think of it that you look on a lot of documents and a lot of resources, and you need to compress it to one card with very specific arguments and 12 topics. And we show that if you train models to this kind of compression, they bring much better results, and they can have very general capabilities. So this is one work, and the other work is how can we actually use it in order to build a perfect debater, and what does it mean perfect debater versus a human debater, and how can we compare the two. Okay, yes, so let's stop here. I didn't talk about chess, by the way. If you want, you can look on our work about chess and the difference between representation of human versus chess, and how we play differently, and how it's related to compression. Yeah.
Okay, so
Thank you.
so let's try to squeeze in a few more questions, because there seems to be a lot of interest. So Gadi is here asking, can an LM help us to be less biased and exclude media noise in media and social network, or maybe because it is trained by human data and work in human representation, and it can't be objective and need regulation? You can also read in the webinar chat, Ravid, the question. I have to admit, I'm not sure that I 100% understood the question. So I don't know if you can you see it, Ravid, the question?
Yeah, I can see it. So I think I will try to answer about biases. I'm not sure if this is like the if this is the question, but I would try to answer, and if not, you can ask again. So I think biases are it's very fundamental concept and very important. And the question, what does it mean, biases? It's very unclear. And for example, like, I don't know, if you give a watch, if you look on watch and you ask what is the time, like you ask LLMs to generate a clock, right? It will always give you the same time, the same position. Why is that? Because we have, like, all the images on the internet have the same, basically the same position of the clock, the same time. This is just trivial one, right? That's easy to detect. How do we detect biases that are not so easy? It's great question, and I don't think anyone has good answer for it. And what does it mean, and like, can we use these biases? And of course, again, we have biases. We train these models on human data. It's not clear how to remove them. There are work to try to remove them, but it's open-ended question.
So there is another question from Sharma. It was asking, do you see alignment between LLMs and humans as shifting LLMs from statistical compactness towards human-like adaptive richness? And are there any metrics to capture this transition, to capture this shift? So interesting.
I'm not sure that I understand. Do you mean like shifting, like newer model? Like, what do you mean?
My understanding, and Shava, if you want to clarify, please go ahead. My understanding is that if you have like the human, I would say, understanding and LLM kind of understanding, so would there be like some kind of a, I don't know, some kind of a continuous way to go from this to that? Can you make like a machine
Yeah,
which is a half LLM, half human?
yeah. So it's a good question. Like, and then if you can create a machine, right? If you can take the AI representation to be more human, so probably we can play with that, right? This is a trade-off, and we can play with that. But first, we need to understand how to shift it to be more human.
Mhm. Okay.
Um,
And another question from the very active anonymous. Is the anonymous attendee always the same one? So this is a good question. By overcoming these inefficiencies that you mentioned, can we achieve system two-level understanding as mentioned by Jan LeCun in AI?
it's a good question. It's a good question. It's not clear what does it mean, system two, and people are really like to use this term, and in principle, yes. Okay, so okay, I will try to. So as I know from some talks with Jan, his understanding about you need some representation, some role model that you can actually use for these models. Okay, and it would be like prediction, not in the input space, if you want, or the output space. And now you can ask, okay, so if I'm not tied to the output, then it may be that I can change my representation in such a way that it will be like it will contain more information, will be richnesses, and it will maybe be more similar to humans, and then we can be more similar to human, like we can train models that are similar to humans. It may be. I don't know. I think it's like at the end there are a lot of details here. There are a lot of details that it's hard to understand if we can actually um, make them. And LLMs, and more specifically next token prediction autoregressive LLMs, are decoder only ones, are very good and very efficient in training. Okay, this is something that we are not appreciating enough. Like if you scale up the data, if you scale up the models, it's still quite easy to train them. And I think this is something that is very unique to LLM, autoregressive LLM, and it's not clear if you can have it in other types of models. So maybe.
Yeah, so we are almost at the top of the hour, and I just want to, since I work in the medical imaging field, and I think that one of the challenges there is to see how you don't really, you assume that you can, and you don't want to replace the medical doctors, but you want really to assist them in their decisions making. So I'm thinking maybe if we really have to pinpoint where exactly do we have to provide AI tools to complement the human capabilities. And I think that this is it's a challenge, because I'm not sure that it's always very clear how you make this complementary I would say a solution. And Sharva is asking if we can share the papers you mentioned about chest. Okay, so the idea sounds interesting. So I think maybe because we are going to send out the recording of the webinar, etc. So maybe we can offline, Ravid, go either look ourselves at your website, or maybe you can share with us, and we will add it to the email that we send all the participants.
Sure.
Okay, great. So wow, Ravid, thank you so much. I think
Thank you.
it's super interesting. I also I wanted to mention it in the beginning of the webinar, but I forgot, and I want to mention it now. You know, I had the privilege to know Tali Tishby, who passed away a few years ago. He gave a fantastic talk at the IMVC about the information bottleneck, and I think that you are so privileged to work with such a great team of people, including Tali. So it's good to see his work alive and kicking.
Totally true.
Yeah.
Yeah.
So, Ravid and everybody, thank you so much for joining. We will send the recording of this session, and yeah, I think it gives us a lot of things to think about. And thanks again.
Thank you so much. Thank you.
Bye-bye.
Bye-bye.